lunchtime, whatever we're doing. Hi, hi, hi. We got 2 roomers here. We have 1, 2, 3, 4, 5 Zoomers, I see, so about half the class here. We have, let's see, 1 more week before break to make it through, and then we get to take a breather. Yes, everyone is happy about that, I'm pretty sure. And let's see, outlines are due Monday. Any questions on those? If you're not sure what to do and want ideas, I'm happy to chat with you individually to help make research questions or otherwise give you some inspiration if you need some. Ideally, though, this would be data you already care about with questions you already want answered. So it would be maximally useful. And if this project overlaps with other projects for other classes or master's theses or dissertations, good. I am a fan of double dipping, okay? Efficiency is fine. In college, as an undergrad, I once wrote a paper for an English class, and then I translated it into Spanish and turned it in for my Spanish class the same semester. I was really proud of myself for that. So, not sure if that's completely ethical, but I was taking 18 hours and working 30 hours a week, and I had to, something had to give somewhere. But so if you have something already that you're working on, and you can use this project as a way to move that forward, great. That's the ideal situation. Nothing due on the Monday of break, obviously. We'll have a formative assessment due the Monday after break. I will put that up next week once I figure out what I want to ask about, and then you can use that as a way to get your head back in the game for the remainder of the semester. So, I will also let you know when homework 3 is available. That is based on, actually should be example 3. It will be the MLM version of the accelerated time model, so you'll be using Elmer and Mixed for that one. So any questions on upcoming activities, responsibilities? Good. All right. Then we're going to talk about structural equation modeling for longitudinal data. That's what we were talking about, right? Sound familiar? What is the biggest difference in terms of how the code and models get set up if you're using the multi-level side versus the non-multi-level side? Do you remember this point? There's one really salient difference that sort of colors everything else. There's no between and within. That is a salient difference, not the one I was thinking of. Go ahead.
Wide versus long data.
Yeah, wide versus long data, that is the biggest one. So that has tentacles that span throughout these things. And the lack of the between and within then makes it harder to figure out what should be a level 2 thing versus a level 1 thing or a smushed thing. So there are a great number of longitudinal models that estimate smushed effects, and that's only recently started to be understood because the people who write in the multi-level world don't necessarily talk to the people who write in the SEM world. So the connections across those things are still being worked out, I would say. But the wide data colors the syntax quite a bit. It also then locks you into balanced time. So if you have unbalanced time, trying to find software that will address that and give each person their own individual occasions is going to be a little trickier. Lavon does not do that to the best of my knowledge. So we're going to look at M+ for the old people data, recall, fixed quadratic model, just time in the level 1 model because that's easier to interpret and less likely to be wrong. So I am using a command in M+ to restructure my data. This is analogous to reshape in R, or what is it called? I think it's called reshape in Stata too, isn't it? Does that sound right? It's something very close to that. If it's not exactly that, it's close. In M+, they have long to wide, which is, oh, got a thumbs up. It is reshape, good, thank you. So it's long data where it's 1 row per occasion per person to wide format, or what I sometimes call multivariate, which is 1 row per person. So this is doing the data transformation for you. The order of operations here is a little bit tricky to keep track of, though. So what it wants first are the columns that are currently in stacked long format that you want to transpose. So I have recall and I have time. So I would not necessarily need to do time if, actually, yes, I do. I need to do it so make sure that's in the right order. Otherwise, it will not handle missing data appropriately. So then what do I want them to be called? So I have named these recall 0, 2, 4, 6, and 8 in recognition of how many years apart these things are. So a unit in this data set was 2 years. So I'm having it organized this way to keep track of that. I am then creating time variables. So if each person was measured at different occasions, if we had unbalanced time, we would need to have these things as part of our data so that we could tell the model, these are the values to be used. I think I have an example of that coming later in the semester. So this will be just pretending the time is balanced for right now. ID variable, it wants you to know how the rows should be grouped together. And then repetition, what it was called previously in the long format file was called occasion, and these are the specific values that I have in there. So this is taking my long data set and making a set of new variables for recall, 5 of them, a set of new variables for time, 5 of those, and 1 row per person. So any questions on that? All right, then, even though we just wrote this code to change the data set, now we're going to pretend like we didn't write that code, and we're going to go back and talk about the original data set. Not confusing at all. So under variable, it wants to know what were the columns in the original long file data set. But then use variable wants to know what the ones are now that are going in the model in the wide data. So that's why I have the 5 recall observations in here that I created with this previous step. So it took me a minute to get this right. If you get hung up on this step, you can always reshape your data in whatever package you use and then just export it for M+. I often do that for things where there's going to be like a lot of variables and it's going to be a pain to list everything out. Missing data identifier as usual. Type equals general estimator equals ML. And then another one that is not possible in most versions of MSEM. I think they added it in Bayes maybe, the standardized solution. So in structural equation modeling, the unstandardized solution is what you get when everything is in units. So those will be variances, regression slopes, covariances, that kind of stuff. In the standardized solution, every variable in the model is transformed into a z-score metric, mean 0, variance 1. And so then we end up with correlations instead of covariances, and correlations or slopes, factor loadings would be in a correlation metric. So this would be like where we could see the correlation between the random effects if we wanted those, correlations among the residuals if we wanted those. So I added this to the output. So this is an empty model, okay? Empty 2-level model. Note there's no between and within, so it's all just under model. I am first shutting off all of the intercepts for the 5 outcomes. So this is 1 variable conceptually, but it's 5 columns in your data set, recall. I am shutting off the intercept that would normally by default be estimated for each one, so that that information is going to be captured by the latent variables, the random effects, and the fixed effects instead. So it's redundant. It will break it if you try to do both. I am also constraining the variance for the residual at each occasion to be the same number. So resvar is both a label and a constraint. I don't have to do that, but I'm trying to make it match the MLM setup as best as possible. And then by, do you remember what that does? That's our one new vocabulary word. We had on, which was slopes. We had with, which is covariances, and we have by, which is people who've had SEM before. Take pity on those who haven't and answer the question, please. What does by do? Two-word phrase. First word starts with an F, second word starts with an L. Oh, close. Latent instead of factor.
Factor loadings.
Factor loadings, there we go. Yep. So I am making myself an intercept factor. That's why I called it int. And I am letting each variable have a factor loading of 1. That is analogous, when we look at the equation, to saying that there is no variable that U0 multiplies. There's an implicit 1 here as what would go with it. So I'm estimating the variance of the intercept right here, and I am estimating the fixed intercept as the thing in the brackets. So I have this labeled as to what it means in traditional multi-level way of talking about things. The intercept is part of the level 2 model in this case. And the residuals for the outcomes, the 5 boxes, are part of the level 1 model for the R. Okay, how are we doing so far? Okay so far?
Can you re-explain the factor loading part?
Yep. So I am creating, I'll go back up to the equation. I am creating beta 0. I'm calling it int. I could have called it beta 0, but I actually don't like it when people name things like in ways that are not obvious. So I'm calling it intercept, beta 0. And beta 0 isn't multiplying anything in connecting to recall. So the way that I accomplish that is essentially like putting an implicit 1 in here, having the factor loadings have a loading of 1, so that beta 0 predicts the outcomes directly, not as a multiplier of anything. That will be in contrast to the next model where we add time, and then we have a variable that is multiplying the circle, and so then we'll need something else in the loading spot for that. Okay, does that help? Okay, cool. Thank you. All right, so the output for this empty model, considering it only has 3 parameters, is quite voluminous. And by the way, there are defaults for growth models that you can use that shorten the code, but I'm not going to use them so that the code is clear about what is being estimated and what is not. So the factor loadings right here are fixed to 1. Do you remember what 999 means? Is that a number? It's not a number. It is essentially a missing data code. So anything that you've fixed where there's no estimation happening, there's no standard error, it just gives you a 999 in these spots. Then we get into means for int. That's gamma 0, 0, that's my fixed intercept. So the mean of the intercept factor is the fixed intercept. The intercepts then for the 5 outcomes are shut off. So essentially what we're doing is, rather than letting each of these variables have their own mean, we're saying they have to share a mean, and we're giving it to the latent factor instead. That's the idea. Otherwise, if I let these intercepts be estimated, then there would be no way to give a fixed intercept as well, because that would be redundant. There'd be too many parameters. Then we have variances of the intercept. The 10, that's my level 2 intercept variance. My residual variance is 5, and those are held equal. So this is an example of a constraint. You would want to make sure in your output that the numbers you intended to be equal really truly are, that it read your constraints correctly, that sometimes that goes awry. And I also have down here another piece of output, the standardized solution. The R square, as it is called, for these outcomes is equal to what works out to be the intra-class correlation. The proportion of variance that is, and I'm going to use air quotes, explained. Internet, I'm using air quotes, okay? I did not really say explained. The proportion of variance that is explained by the random intercept. That's another way of saying intra-class correlation. All right. Next one. You want to see some slopes? We're here. Why not? So just fixed slopes. So I'm adding time and time squared to the model as fixed effects only. This is the MSIM version. All right, here is our version. So all of the first part of this, the data unstacking process, that's all exactly the same. I just have it in here for make sure that folks know that it needs to be done first. Now I am adding to the model these ones. Aha, I did do it here. Time, 2, 4, 6, and 8. So these were created as the individual time values that I had in the long data, extracted out to 5 columns. And I am using them in a command called t-scores. So this is how you tell it, hey, take the loading that for the first factor loading and fix it to that, whatever that value is in that person's state, for that person's row. So we have individually varying factor loadings being allowed here. and I still have recall for the 5 boxes here. So here's some shorter code. If you want to fit a quadratic model, M+ anticipated that. So I'm still fixing all the per occasion intercepts to 0 so that their means go up and are captured by the latent factors. I am still forcing the level 1 residual variance to be the same over time so that it's comparable to the previous model. And now I am building, in this one line of code, 3 latent factors. The order of them must be this way for this code to work. It knows what you're trying to do. So it's fitting these factor loadings at those variables, and it is going to build me an intercept, a linear slope, and a quadratic slope out of them. It's doing all of that for me under the hood. So the loading for, say, the linear slope at the first occasion is going to be whatever is in that column. The loading for the linear slope at the last occasion will be whatever in that column, and then all the ones in the middle will fill in as well. Now, in the level 2 model, I am giving each of those latent factors a mean. So I have a beta 0 mean, a beta 1 mean, and a beta 2 mean. That works out to be the fixed effects. However, I do not yet want random slope variances, so I've shut those off. So the only variance that I'm referring to then is for the intercept, and that is a default. Okay. Questions on any of that? For something like a piecewise
Can you
model,
go
this would not work.
over
Go ahead.
that part, like how you make the quadratic? Yeah. Just read it over, please.
You got it. So this is an example of something that M+ creators developed to save typing, but it's completely not obvious what's happening. So your confusion is very well justified. There in the manual, it says if you want to fit a quadratic model, you can stack up your variables like this, and it essentially will do the multiplication for you. So it is doing, under the hood here, it is putting 1s for the intercept factor as the loadings, and then it is putting these time values for the linear factor as the loadings, and then it is squaring them to put the loadings for the quadratic factor. So this is a 3-bubble model. Let me get to the picture that goes with this. This is what's happening implicitly. I have an intercept factor. Its loadings are all going to be fixed to 1. I have a linear factor. Its loadings would be fixed to whatever the time column would have been. And then if I square those values, the loadings for the quadratic are fixed to that. And that must be the case because in my level 1 equation, I have a variable that is multiplying beta 1 and beta 2. So that's why these loadings need to be some number that conveys how much time has passed. Okay, does that help a little bit? Ish. I accept it. I accept ish. So if you wanted to do, for instance, a piecewise model, you could do that by fixing the loadings to whatever pattern created the first slope and the second slope. But as far as I know, there's no analogous way to do that using this. I don't know how to tell it to do that. So I think theoretically it should be possible, but I have yet to figure it out. Okay, so we have random intercept but fixed slopes in this case. So that means when we come down here, we have 3 means. What are those called otherwise? In this context, what would I have called them last week? Or last semester? Fixed effects, ding, 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 that's what these are, okay? So the mean of the lin factor is the fixed linear time slope. The mean of the qua factor is the fixed quadratic time slope. And again, qua because it's 3 letters. Intercepts still shut off. Intercept variance is being estimated, and the ones for linear and qua are shut off. So what would I have called these things last semester? The variance of my latent factors. Random effect variances. Yep, that's what these are. And what would I have called this last semester? Leftover. Yes. Also one more. Yes, leftover level 1 residual. So residual in both ways of thinking about it is what this refers to. The M plus is saying it's predicted. That's why it's leftover. But I would call this level 1 residual. So conceptually, that's what this represents. Okay, want to see a random slope? You know how to do this.
Can I ask one question first?
Yeah.
For the t-score part where you're like assigning their exact time value, would they have to have all of the 8 times or whatever? Like, does that code work if you have people that don't have all of the same amounts of occurrences, I guess?
The code will work so long as you have a column for everyone, and then each person's values can be filled in or not. So it won't use the observation that doesn't have a corresponding time value, but I'm guessing that's because you wouldn't have a corresponding outcome.
Okay.
So yeah, it has to be structured as if it's complete, but it doesn't actually have to be complete. Yeah, this is where the rules about missing data get a little fuzzy. Because last semester, the rule was all the rows have to be complete to be included, but this is a definition of a row that's per person, not per occasion. It's a joint likelihood, not a conditional one, right? Yeah. So we can have missing data on outcomes as separate columns. It's directly analogous to missing data on rows. We still can't have missing data on predictors yet. So that's why if you're missing a time observation as a predictor, then that would not go in, but you're probably missing the outcome anyway. All right, so let's see. Oh, no random slopes yet. Cross-level interactions first. So adding age cohort as a predictor of the intercept in a linear term and a quadratic term, adding age cohort as a predictor of the linear slope. Scrolly, 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 scrolly. Okay, so I have 2 new variables that I created for this using define. So I have age at time 0, which is my cohort indicator, centered at 84, and then I have the squared version of that. Those go into the use variables out here. So note another thing that's different about the setup of the variables. Remember before when we had the multi-level version of this, we had a between entry and a within entry, and you told it, put it only on one level or the other? Like, we don't tell it that. So M+ doesn't know, essentially, whether these things are people things or time things. It's not relevant to the specification of the model when you do it this way. Still keeping the slope variances out of the story for right now to match the model, but I'm adding in cohort predicting the intercept and linear change, and cohort squared predicting the intercept. What would I call this piece? Actually, do these one. This one and this one. What would I call that last semester? What's happening? I'm out. That person really didn't want to play. What would I have called this? Close. It's predicting int, which does not stand for interaction in this case, although it could. What would I have called this last semester?
Is that at the cross level?
Say it again.
Is that the cross level part?
This one is the cross level. So that
Okay.
means this one would be what? I think you're all overthinking this. What do you call it when a predictor predicts an intercept?
A regression.
Yeah, like a main effect. This is the main effect of cohort. And this is cohort predicting linear change in a cross-level interaction. I know. It's like a different world. It is really the same, though. It's just different notation, different code, and different language, but the same ideas. So then this is a main effect of cohort squared in predicting the intercept. So main effects do this, cross-level interactions with time do this. Okay. Ready for one more? Do we have the strength for one more and then this handout's done? Okay, I think we do. We're adding in a random slope for the linear term. So scrolly, scrolly. That's the MSEM version. And here is ours. So if I want to add a random slope, I don't need to change anything with respect to the variables involved. I'm just adding a new parameter. And we'll play spot the difference. What's changed in the code that gives me a random linear time slope?
That would be int with len.
Yep, one thing right here and one thing right here. So this len used to be at 0, meaning don't give it a variance, just keep it as a fixed effect. And I'm saying, no, I'd like a variance now, please, which is the default, but don't give me one for quadratic. And because I now have 2 random effects in my model, I need to have their covariance, and that is a default when you do it this way. By the way, there is an option that you will see me use later in the semester that changes the defaults. So there is an option called, I think it's like model equals no covariances that goes here, and then that shuts off all default covariances so that you can only turn on the ones that you want to have. So sometimes it's faster to do that and then just write the ones you want than to spend all the time shutting off the ones you don't. It just kind of depends on the problem. So model equals no covariances is the option that would go right here to do that. And let's find it. Oh, no, that was the yelly one. Come back. Is it? Oh, that's interrobang. Yep, I went too far. Here we go. So the new terms then, what's that? What would that have been called last semester? Int with len. Covariance, yes indeed, between what and what? Yeah, random intercept and random slope. Yeah, almost in stereo. Yep, that's what I would have called it. And note that qua is listed under variances because it's unpredicted and it doesn't have any. That's what the 0 means here. Whereas int and len are under residual variances because they're being predicted. Now, would I have called these residual variances last semester? Nope. Some people do, though. Like, you will see textbooks talk about level 2 residuals and level 1 residuals. Level 2 residuals are U's. I just don't use that term because I find it confusing. So these are leftover level 2 variances. The ones for recall are leftover level 1 variances. And they're all stuck in the same column, same section. I think we hit the rest of those from the last time. And here are the cohort effects that we had introduced on there. So any questions? All right, I don't remember what happened for the interrobang one. I think it wouldn't even run. Yep. Nope, okay. Bye-bye handout. Hooray. Back to slides. So what we just did is walk through the analog of, let me go back here. So MSEM, long data, walking through the wide data version for that example. Now some other stuff that I want you to have seen. So this is what it would look like in a path diagram for the SEM model where we have a level 2 predictor. I just said SEM model, I did it. That's how tired I am today. I'm ready for spring break too. Level 2x is predicting the intercept, the time slope, and the quadratic in this example here. If you wanted to go the other way, then this is the point where you could not estimate this model using Elmer or mixed. It would have to be some kind of multivariate opportunity. Multivariate is the key, folks, not SEM per se. You just need some way of predicting multiple outcomes at the same time. So we have 5 outcomes on the bottom here for our 1 row of data per person. I have another column that would be level 2x that's being predicted. And I have a link in here that you can't see very readily, but you can see the underline, to one of the papers on your reading list that just came out. It is showing the downstream consequences of centering with respect to time in terms of how the prediction of this outcome happens. It's actually more complicated than you would think. Because when you're having intercept, linear, and quadratic slope as predictors, they fight against each other. Like predictors, slopes are the unique effects of that predictor holding the other ones constant, right? So what does it mean to have like linear time predicting, controlling for quadratic time, and quadratic time controlling for linear time? Like that's a little weird. I'm guessing that neither of these would have significant unique effects because they have so much overlap, particularly given the centering with the first occasion or the last occasion. The same is actually true for this. Like what this intercept represents is expected outcomes at the occasion where all the slopes contributing to the model are 0. So it's this one. So if you centered this variable, if you centered time differently, this variable takes on a different interpretation, right? Like if time 0 was the end, then this would be individual differences at that occasion. That's a different variable, would have a different relationship to level 2x. So it gets a little tricky to go this way. And so there's some caveats that I think are important to mention that this paper discusses, which is why I added it to the reading list this time. But this is when you would need to do some kind of multivariate software to be able to predict something else. Okay.
Possible to predict a like level 2 predict, like if that was a time varying predictor instead of just one box. Is that a possible thing?
Yes, it is. However, most people do it wrong. Would you like some foreshadowing to answer your question? Okay. Let me get something open from last year, 2 years ago, last time. Looking for one. I have to have it in here, don't I? Oh, I don't have it in here? I have to have it in here. Nope, it's not in here. Let me find it. There we go. Didn't take long. There's one that's wrong. I am a human, I promise. There we go. So we have time-varying predictors here in the boxes, and we have time-varying outcomes right here. Now the problem. These paths, are they the between effect or the within effect? Yes, they are. However, the reason this is not wrong, and this particular person would know better, is it works out that if you allow these time-varying predictors to correlate with the intercepts and slopes of another outcome, it switches them to within. Yeah, it's like some kind of voodoo magic. But if you don't do that, then these are smushed paths. Now, do you think that we're looking at, I guess, alcohol symptoms and marijuana symptoms? Do you think that those would change over time, maybe? Yeah, we might need, like, whatever this construct is that's varying over time might need its own time slopes as well. So then you'd end up with this one and this one for that as well. And then you get into something like this, where you have an intercept and slope for one variable, an intercept and slope from the other. The ones in between can have within paths, and then you can have between paths connecting these guys. Does that help? That's coming. It's like, oh, I want to do that. Do you want to do that for your project? Maybe.
Potentially, yes.
Potentially? Okay, yeah. Well, we will have covered it by that time. That's what's coming up after break. All right, I have some examples on wide data of how you would write out the quadratic model in balance time. So what the pattern of loadings would look like that's being accomplished for you in the shorter version of the code that I gave you. If you're using lavaan, here's how you do that instead. The only catch in going back and forth across lavaan and M+, is that in M+, a star means estimated, and in lavaan it means fixed. So whoever did that, thank you for making more job security for us. All right, so considerations then, when you would do things one way versus another. For unbalanced time, we need this idea of definition variables. That's the t-scores option in M+ that allows us to save the columns of when the observations were and feed them into these factor loadings right here. Another option that in wide data SEM like this, you can fit a model where it empirically tries to figure out how much change has happened, rather than you saying, I'd like quadratic or linear or whatnot. That is called latent basis. So let me show you how that works. So this thing that is a slope doesn't have a name anymore, because we don't know ahead of time what kind of slope it's going to be. It's going to figure it out for us. So the term for this is called latent basis. Latent meaning imaginary, like you figure it out. What's the basis of this? Well, it's not linear, it's not quadratic, it's not piecewise, it's not exponential, it's to be seen. So you can use constraints in various ways. The most common that I've seen is to fix the first occasion to 0, fix the last occasion to 1. And that, 2 of these have to be constrained for this model to be identified. And the other loadings get estimated. So if you do it that way, the loadings would represent the total proportion of change that has happened by that occasion, where a unit is the whole study. Like the change is between 0 and 1, that's a unit. So how much time has passed is not really part of the story in that sense. Or, like for something like this, where a linear slope would have been 0, 1, 2, 3, 4, if you set up the pattern like this instead, 0, star, 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 4, then it's on the same scale in terms of like a unit being 1 distance apart. So then you can test, for instance, if I fix the loadings in between here to 1, 2, or 3, does that make the model worse? If it makes the model worse, then a linear slope doesn't fit, and it needs to be some flavor of nonlinear to be determined by these factor loadings. So I like this strategy for situations in which you only have maybe 3 or 4 indicators. If you only had 3, then only 1 latent basis could be estimated, because you don't really have enough information to do multiple flavors of random slopes for change over time in that case anyway. And I also like it for avoiding the problem, a couple slides ago, this one, avoiding the problem of having linear and quadratic time fight it out for shared variance. If there's only one type of slope, and it's a nonlinear slope, then like the interpretation of what it's doing to predict something else is going to be a little clearer and easier to follow. So I like it that way. Just as an aside, there is the potential for random latent basis slopes. I know, that sort of breaks my brain a little bit. But the idea is that even though these things are estimated, they're fixed. Meaning, like, let me get some numbers on here. I think I have. Do I have numbers on here? I thought I did. You'll see some in our example. I have a latent basis model in example 4b. But like if this is, say for somebody, this is 0 on average, this is maybe 0.5, this is 1 and 1. So that would be like a function that climbs up and stays there, something like that. Well, do you think that's going to hold for everybody? Probably not, right? We've been talking about individual differences in change. So maybe someone else's loadings needs to look like, 0, 0, 0, 1, like they jumped up later, something like that. So random latent basis loadings are theoretically possible, but you have to hack the between within syntax to do it. So there's an article with M+ code in it if you're interested in doing that. So the difference in the code is stars for where we used to fix these to specific time values. So you just ask it to figure out what the loadings are. And the same is true in lavaan, except there's no stars, because stars mean fixed. So if you're using Lavon, I can help you with that. I have some examples in the SEM class using Lavon too that I can guide you towards. So trying to wrap this thing up then, multi-level models, where we started. Pros and cons of doing things this way. In this approach, we have long data. Person dependency is captured using random effects, which means we're adding levels. So a level means some kind of estimated variance for that sampling dimension. These have the advantage of having REML estimation, which is better for smaller samples, along with the use of denominator degrees of freedom instead of assuming infinity. But they're limited in that random effects can be predictors. Like I can't have my time slope go and predict something else in Elmer, it doesn't work. And predictors can't have missing data. It is a conditional likelihood, meaning you have to have all of the predictors to build the prediction to have the residuals to figure out how much variance there are. So that's a significant limitation. MSEMs are still working the same way as univariate multi-level models. So functionally, it's just the same, like an Elmer call for more than one outcome at the same time. Like it works the same way. It can be better for time-varying predictors. We'll talk more about that in the weeks to come. And it can be easier to include random slopes for level 1 predictors than in single level SEM. I've had it break doing it this way and not break doing it the other way. Regular flavor SEM then, or what I would call single level SEM, we're capturing person dependency with latent variables and wide data. So all of these separate occasions are separate observed variables. It may not work for unbalanced data because you need the software to be able to understand what the time loadings should have been. If you have balanced data, though, you can easily assess absolute model fit, just as in any SEM, so that's considered an advantage. By the way, do you know what happens to model fit when you have unbalanced time loadings, like when you use the t-scores? It goes away, because there's no answer key at that point, right? If you think about the unstructured matrix as your answer key, what the variance should be at each occasion, what the covariances should all be, if you have unbalanced time, then that's a whole lot of rows and columns, and it becomes unwieldy. So for nefarious purposes, you could invoke t-scores even if you didn't really need it so that you didn't have to worry about misfit. I say that tongue-in-cheek, not recommending that, but one could hack that for their personal gain. But for most of you, the models that you'll be doing in your projects, you're not going to have absolute fit, is my guess, because you're going to have unbalanced data or random slopes or some other way that we don't have an answer key anymore. And if you need to test longitudinal invariance, which you should always do when you're working with latent variable models of this, we need to do it this way. That's what we're going to do next. Unfortunately, the cons is that it's a lot easier to smush level 1 and level 2 together, as you've seen, because there's no strict demarcation of what's in the between model or the within model, nor are there definitions of what kind of variables you have in your boxes. It doesn't know or care whether it's a level 1 thing or a level 2 thing. That's up to you. All right, I added 2 slides. This is from the lecture that's forthcoming, but I added 2 slides because I wanted to give you pictures to work with this. So in example 4B, I'm going to show you a curve of factors model where we have lower order factors that indicate some kind of trait at an occasion, and we're going to introduce higher order factors to examine change over time. So this is a long way of saying we're going to look at change in latent variables as outcomes. So it answers the question, do I have fixed or random change over time in my conceptually one latent variable, assuming all outcomes change the same way? This requires at least partial longitudinal invariance, meaning that the trait relates to its observed outcomes in the same way over time. So that's the first step that we have to do, is to test that. If that falls apart, though, I should say when it falls apart for some of you, unfortunately, then you can pursue an alternative version, which is a factor of curves. These sound like synonyms, don't they? They're not. They're 2 very completely different things. In this case, what we're doing is the opposite in terms of what's lower versus higher. So in this one, we first fit a growth model for each outcome. We then look at the correlations among the intercepts and slopes across outcomes and see if they're consistent with the idea of a common higher order factor. And then you can fit those in the model. And this is advantageous if longitudinal variance is not going to hold, or how people change depends on what indicator of the construct that you're looking at. So here's some pictures. This one on the top here, this is curve of factors. So conceptually what is happening is we have boxes for time 1, I have 3 measures of something. I have 3 measures of something at time 2, and time 3, and time 4. So then the thing that I'm trying to fit the growth model of is this latent variable that they've called eta. So squiggle, this is squiggle 2 up here. I don't know its proper name. I never will. I refuse to learn it. This is squiggle 2 as opposed to squiggle 1 because it has 2 curly cues at the top. That's why it's squiggle 2. I'm assuming this is an intercept because of the pattern of 1s. And this one over here looks like a linear slope because of this pattern. And note there's sort of like an implicit arrow that's missing here that would be 0. So the idea then is we have a measurement model so that we can better represent a latent trait using multiple indicators at each occasion. Then we're going to watch that latent trait grow. The stupid triangle is used to put means into the picture. I'm not going to use that. But in order to watch a latent trait grow over time, it has to first be the same latent trait over time. Does that make sense? Like how the indicators relate to the trait needs to be the same over time. Otherwise, it's not the trait that's growing, it's that the trait is becoming a different trait. And then growing doesn't make any kind of sense. This would also break if you had separate indicators, like if you didn't have overlap. If you measured the trait differently at time 2 than in time 1, with different indicators with no overlap, you're dead in the water. I think I told you a story about that last semester. Once helped on a project in graduate school where someone wanted to give age-sensitive measures, and so they gave a different set at each occasion. The ones that were most appropriate for 3rd graders, the ones that were most appropriate for 4th graders, and so on. But they had no overlap. And the solution that I was told they were going to do is to put everything into a z-score metric, and that would put them on the same scale. Anyone see an issue with that? Is that going to work? No, z-scores don't grow. It's like I have an apple and an orange and a lemon and a pineapple, and I'm going to see how fruit changes over time. It's like, what? No. So you don't have to have exactly the same variables. You could weave them in. So like you could have A, B, and C here, and then B, C, D here, and then C, D, E here, and kind of like go like that. Then this can work. Then you would need to enforce invariance constraints on the common ones over time to kind of glue it all back together again. So there is a way that you can change your measures over time and still measure growth. The planful overlap is the key to doing that. It's called vertical equating in the IRT world. There's another one too. I can't remember. What do they call that over in IRT world? Vertical equating is the one I'm thinking of. What's another one?
Scaling?
Vertical scaling, yes, that's another one. So, yeah, connecting the scores over time through planful overlap. So if you have at least partial invariance, you're measuring the same trait over time, then you could do something like this. When that falls apart, here's an alternative. I didn't get a chance to show this last year. I built it this year, so we're going to do it. This is the conceptual opposite. So here what I have is a growth model for x, here's my intercept, here's my slopes, a growth model for y, a growth model for z. Then I could estimate covariances among these 6 things. And maybe the intercepts are all highly correlated, and maybe the slopes are all highly correlated. If that's true, then I can introduce these things up here, what are called higher order factors or second order factors, for a common intercept and a common slope. So then it's like, there's this thing that causes each of the intercepts, and the intercepts then cause each of the variables. So it's explaining the pattern of covariance among the intercepts and among the slopes with latent factors. And that represents a testable hypothesis as to whether these things sort of go together in terms of how they change over time. So there's an article on your reading list about this. There's an article for this one as well. If you want to do something like this for a project, this would be fair game. Just getting this stuff to run is surprisingly challenging. I will tell you that. And as you might imagine from the pictures. And yes, these pictures take forever to make, and that's why I steal them from other people whenever possible. But you'll have to make your own. All right. So let's take a look at, not that one, example 4B. We do get to start it. Don't save.